Okay, in this video I want to talk a little bit about improper integrals. So let's first start by talking about what an improper integral is. So we say an integral, the integral from a to b of f of x dx, for example, is improper if it meets one of the following conditions. So if a or b is positive or negative infinity, like this example here, I have the integral from 0 to infinity of e to the minus x dx, okay? If f is discontinuous at a or b, so like the integral from 0 to 1 of 1 over x to the fourth dx, notice that at 0, 1 over x to the fourth is discontinuous. There's an infinite discontinuity. And then if f of x is discontinuous between the bounds, like the integral from 0 to 2 of 1 over 1 minus x squared dx, notice that if I plug in x equals 1, so 1 is between 0 and 2, and this function 1 over x minus 1 squared is infinitely discontinuous at 1. So it's discontinuous between those bounds. So next I'm going to show you kind of what we do in each of those cases. So to be proper, we can't put infinity in the bounds because infinity is not a number. When we specify bounds, we're specifying numbers of an interval that we're integrating over. But it's not really proper to say, okay, the integral from 0 to infinity. So instead, we write this integral. We'll take this one, for example. We write this. We'll write the limit as a goes to infinity of the integral from 0 to a of e to the minus x dx. Okay? Now notice that this is just the limit of an integral that I can actually evaluate. Namely, this is the limit as a goes to infinity of the integral of e to the minus x is minus e to the minus x. So minus e to the minus x evaluated from 0 to a. Okay? So we could evaluate that, and I leave that to the viewer to evaluate that and see if that gives you a value. It's worth mentioning that if I have an improper integral, so in general we're talking about improper integrals, so if f of x, or the integral from a to b of f of x dx is improper, if this value, if the integral from a to b of f of x dx equals a finite number, so if it equals like 1 or 2 or pi or whatever, if it equals a finite value, we say that it converges to L. We say that it converges to whatever finite value it has. If the integral from a to b of f of x dx goes to infinity, or plus or minus infinity, I should say, so if it goes to positive or negative infinity, we say it diverges. So in other words, it diverges if and only if it does not converge. Okay, that's important terminology. So I leave it to the viewer to see if this value here will converge to a limit or if it will diverge to infinity. So the other example is if f is discontinuous at a or b. So again, we'll take this example here. We would write this as a limit. The limit as a goes to 0 from the right of the integral from a to 1 of 1 over x to the fourth dx. Say we go to 0 from the right is because if I look at this function, well, you know what, even better. Let's do this example a little bit differently. Let's say, what if I have the integral of 1 over x cubed? So if I x cubed instead. So that looks something like this. And I'm taking the integral over the region from 0 to 1. So that's this region here. Notice that the rest of my interval is to the right of this infinite discontinuity at 0. So the only way for me to approach 0 is to approach from the right. Because also notice that the limit from the left does not equal the limit from the right, and in general that is not the case. So we need to approach from the right. So we need to be sure that we're specifying which way we are approaching from for some of these problems. And so, again, this is an integral that I can very easily evaluate. So it would be the limit as a goes to 0 from the right of the integral of 1 over x cubed is negative 1/2 1 over x squared, evaluated from a to 1, and we take the limit of that as a goes to 0 from the right. And again, I leave it to the reader to see, or sorry, to the viewer to see if that converges or diverges. Okay? And then additionally, the last example is if f is discontinuous between the bounds, like this integral here. So we need to rewrite this as, we can split it up into two sums, right? So I can have the integral from 0 to 1 of 1 over x minus 1 squared dx, plus the integral from 1 to 2 of 1 over x minus 1 squared dx. Each of these is an improper integral, but I can rewrite them using the method that I used above, specifying using the limit notation and specifying the direction that we're approaching from. So I should rewrite this as the limit as a goes to 1 from the left of the integral from 0 to a of 1 over x minus 1 squared dx, plus the limit as b goes to 1 from the right of the integral from 1 to 2 of 1 over x minus 1 squared, sorry, not 1 to 2, rather b to 2 of 1 over x minus 1 squared dx. All right. Obviously, when we're evaluating these limits here, we're just evaluating this, for example, would be negative e to the minus a minus negative e to the minus 0, and we take the limit of that as a goes to infinity, as we usually would as a normal limit. So now let's do some problems with examples. Again, here's this. We say an integral diverges if a definite integral goes to plus or minus infinity. So let's take a look at this first one here. I have the integral of ln x over x from 1 to infinity. Okay? So I notice that I have infinity in my bounds, so immediately the first thing I need to do is rewrite this integral as the limit as a goes to infinity of of the integral from 1 to a of ln x over x dx. Now, it's worth remarking that it doesn't matter what I put for a. I could have put b, c, d, u. I could have put, alpha if I wanted to. I could have put beta. I could put theta. It doesn't matter. It's a dummy variable. But for simplicity, I just choose a. Now, we're taking the integral of ln of x over x dx. So you can verify by a simple u substitution that this is going to be the limit as a goes to infinity of 1/2 ln squared of x, or I can rewrite it as this, ln x squared evaluated from 1 to a. Okay? Now, this is going to be the limit as a goes to infinity of 1/2 ln of a squared minus 1/2 ln of 1 squared. So plugging things in, notice that the limit as a goes to infinity, as a goes to infinity, ln of a will go to infinity because ln looks like this. It starts growing very slowly as we go out to infinity, but it does grow. It keeps growing forever, so this goes to infinity. So, and we know that infinity minus, in this case it'll be 0, infinity minus or plus a finite number is infinity. So this tells us that our integral diverges. So the integral from 0 to infinity, from 1 to infinity of ln x over x dx diverges. Okay? Now, moving on, we want the integral from 2 to 3 of 1 over the square root of 3 minus x dx. The integral from 2 to 3 of 1 over the square root of 3 minus x dx. So I notice that there's going to be a discontinuity of this function when x is 3. So immediately I know I need to rewrite this as the limit as a goes to 3 from the left of the integral from 2 to a of 1 over the square root of 3 minus x dx. So it's easily verifiable by a u substitution that this is going to evaluate to negative 2 times the square root of 3 minus x evaluated from 2 to a. Okay? And I'm not focusing on the details of that u substitution because I'm more focused on the topic of improper integrals. Now, I can evaluate this limit after I go ahead and do this evaluation. So I will have negative 2, the square root of 3 minus a, minus negative 2 times the square root of 3 minus 2. And this is going to be, I can go ahead and plug in 3 for a by the properties of limits. So I have negative 2 times the square root of 3 minus 3 plus 2 times the square root of 3 minus 2. This will go to 0, so that will cancel. And so I'm just left with 2 times the square root of 1, which is 2. So this tells us that our original integral converges to 2. Okay. Moving on, we have the integral from 0 to 1 of 1 over 3x minus 1 squared dx. So I can see that there is going to be a discontinuity at 1/3. And the reason I see that is because if I plug in x equals 1/3, I have 3 in the denominator there, 3 times 1/3 minus 1 squared, doesn't matter though. And this is just going to be 1 minus 1, which is 0, which will give me a 0 in the denominator. So there's a discontinuity at 1/3. So immediately I see that I need to rewrite this as the limit as a goes to 1/3 from the left of the integral from 0 to a of 1 over 3x minus 1 squared dx plus the limit as b goes to, let's say, 1/3 from the right of the integral from b to 1 of 1 over 3x minus 1 squared dx. So I can go ahead and rewrite this as the limit as a goes to 1/3 from the left. Notice that I never drop the limit notation, because when I drop the limit notation, I'm talking about something fundamentally different. So we never drop the limit notation until we actually plug things in. So easily verifiable that this is going to be 1/3 times negative 1 times 1 over 3x minus 1, evaluated from 0 to a. Similarly, this will be the limit as b goes to 1/3 on the right of, we'll just rewrite this as negative 1/3 times 1 over 3x minus 1, evaluated from b to 1. Okay, so next what I'm going to do from here is I'm going to notice that I have a copy of 1/3 here and a copy of negative 1/3 here. They're both negative, sorry. So I can go ahead and pull that out front. I can factor that out. And so I have negative 1/3 times the limit as a goes to 1/3 from the left of, let's see, I got, evaluating this here, I have 1 over 3a minus 1 minus 1 over 3 times 0 minus 1 plus, I have, evaluating this here, I have 1 over 3 times 1 minus 1 minus the limit as b goes to 1/3 from the right of 1 over 3b minus 1. Okay. And things are going to get a little bit tricky here. So this piece here is 1 over 3, negative 1 over 3 times 0 minus 1. That's negative 1 over negative 1, which will just give me positive 1. This other constant term here 1 over 3 times 1 minus 1 is 1 over 3 minus 1, which gives me 1/2. So what I can do is I can pull those out front here like this, so I'll have negative 1/3. I'll just move my constant terms out here so that I can worry about my limits to the right here. So I'll have the limit, plus the limit as a goes to 1/3 from the left of 1 over 3a minus 1. And then I have minus the limit as b goes to 1/3 from the right of 1 over 3b minus 1. Okay, cool. Now this just becomes 3/2. So I have negative 1/3 times 3/2 plus, and what am I going to do about these guys? Well, what I can do is I can give them a common denominator and add them together. So by the properties of limits, I can do this. The limit as a goes to 1/3 from the left, limit as b goes to 1/3 from the right. So I just brought this over here of 1 over 3a minus 1 minus 1 over 3b minus 1. Okay, now from here, just continuing to solve this bit out here, I will have these limits here. Just go ahead and copy them, that way it's easier for me. So I'll have these limits here, giving them a common denominator so I can add them. I will end up with 3b minus 1 over, so I'm multiplying by what's missing in the denominator, so this one is 3a minus 1 times 3b minus 1. So I multiplied this whole thing by 3b minus 1 over 3b minus 1 to get this here, this whole thing here. And then I have minus, so I'm multiplying this whole thing by 3a minus 1 over 3a minus 1 to give them a common denominator. So I have 3a minus 1 over 3a minus 1, 3b minus 1. Okay, and now I go ahead and write out the rest of this here. This is just carrying things down from the last line. And then now, because they have a common denominator, I can add these two fractions. So I'll have 3b minus 1 minus 3a plus 1, right? Because this whole thing is being multiplied by a negative, over 3a minus 1 times 3b minus 1. Okay? Now, go ahead and write this out so we're being nice and zeros here. Okay. Plus, so appeal to your logical brain here. I'm going to say that this can be rewritten because at this point both a and b are going to 1/3. And even though they're approaching from the left and right, we're still approaching 1/3. So I can rewrite this as the limit as c goes to 1/3 of, I will have 3c, so just replacing a and b with c because we see that they're both going to 1/3, so you can replace them with another dummy variable that goes to 1/3, minus 3c over, this would be 3c minus 1 times 3c minus 1. And then we note that this is just going to be negative 1/3 times 3/2 plus the limit as c goes to 1/3 of 0 over 3c minus 1 squared. Or in other words, 0, right? Because it doesn't matter. It doesn't matter if we just have 0 here. Things will cancel out. So, or in other words, this guy will just go to 0 because what we really have here is 0. Okay, so we can rewrite this now as negative 1/3 times 2/3, which, sorry, 3/2. And these 3's will cancel, and I'll be left with negative 1/2. Okay, so that would be the integral from 0 to 1 of that 3x minus 1 squared, 1 over 3x minus 1 squared dx. Okay, And I know that last step might have been a little bit hand wavy, but it turns out that it does work, and that would be a good example of solving a problem where we have to break the integral up as two improper integrals. Now, if you found this video helpful, please consider liking and subscribing. Thanks.